Question 11. Which semiconductor material yields the highest peak-to-valley current ratio? Gallium arsenide provides the cleanest electrical characteristics and highest ratios for tunnel diodes. Question 12. Under reverse bias, how does a tunnel diode behave? Because the electron bands overlap heavily, it conducts in reverse with virtually zero breakdown delay. Question 13. Who shared the 1973 Nobel Prize in Physics with Leo Szilard for electron tunneling? Ivar Yavor and Brian Josephson shared the 1973 Nobel Prize for discovering tunneling in superconductors. Question 14. Why is a tunnel diode highly resistant to ionizing radiation? Since its operation relies entirely on majority carriers, radiation damage to the crystal lattice barely affects it. Question 15. What is the typical peak-to-valley current ratio for a germanium tunnel diode? Germanium tunnel diodes typically offer a highly usable and stable peak-to-valley current ratio of about 10:1. Question 16. What happens to the current past the valley voltage point? Past the valley point, quantum tunneling ceases and normal thermal diffusion current takes over. Question 17. Why are silicon tunnel diodes rarely used in high-frequency circuits? Silicon has a very low peak-to-valley current ratio, making it unappealing compared to germanium. Question 18. In what famous historic space mission were tunnel diodes heavily utilized? The Voyager probes used tunnel diode circuits because they could survive intense radiation environments in deep space. Question 19. Which curve pattern represents the current voltage graph of a tunnel diode? The current rises to a peak, falls to a valley, and then rises again, forming a classic N-shaped curve. Question 20. What degrades a tunnel diode's performance over long periods of operation? Slow structural diffusion of dopants widens the ultra-thin junction, eventually stopping the tunneling effect.